Well, in this section, we'll review a little bit, probably review. You may have seen the Gibbs paradox discussed before, but if you haven't, well, this will be an introduction to the Gibbs paradox, and if you've seen it, well, it's just a little bit of a review for you. Gibbs, of course, one of the founders of statistical mechanics, Josiah Willard Gibbs, and he proposed the following paradox. He did it in a variety of ways, but this is sort of my interpretation of at least one of the ways. And it basically involves what look to be some apparent inconsistencies in classical thermodynamics to fully explain the mixing of ideal gases. And what he says, well, let's take a look, Gibbs says, let's take a look at two similar systems. I'm going to do it here. Let's suppose that I've got over here a system on the left that consists of an ideal gas at temperature T, and the volume on this side is V, and I've got N of these ideal gas molecules inside this volume V. And they have the mass is M sub A, so I have A-type molecules. And on the right-hand side, here I've got an impenetrable partition. I've got a different molecules. I represented them by O's and the others by X's. But it's at the same temperature, so they're in thermal equilibrium. It likewise has a similar volume, and I have N molecules on this side as well. The only difference is they have a mass M sub B. So type A and type B. And then what we do is we remove the partition between them. So maybe we slide it out or break it, or we could have a valve in here to let particles go from one side to the other. And as a result, the mixing, this is sort of the classical mixing problem, is that now these two ideal gases can roam over the whole volume. And so since it was an equilibrium temperature, it's still temperature T. They have, instead of a V, they've got 2V to roam around in. There's still N of type M sub A, of mass M sub A, and M sub B likewise, it has a accessible volume of V1, of 2V here as well, and 2V as well. So we have these, and mixing occurs, and I've tried to indicate that with these X's and O's that are going to go around. So basically one diffuses into the other. And as you probably know, that's an irreversible process. And one can calculate the total change of entropy that occurs in the system as a result of removing this partition between the two sides. And what I did is I broke it up into a final, so this is our initial state up here with the partition between, and the final state here. And so the change in entropy of the system is the final minus the initial. And the way I did that is I devised it the change of entropy of the A molecules plus the change in entropy of the B molecules from initial to final. And then use a classical result. You probably have seen this in thermodynamics, maybe from last semester or maybe from earlier classes, but from previous classes. As long as I'm at constant temperature, the change in entropy of the system is NKBT times the natural log of V2, V1. So at constant temperature, I only change the volumes. I don't allow any additional molecules in or out of this combined system. And I'm at constant temperature. The general form for an ideal gas, there's also a term that depends on temperature, but it reduces to zero in the case where temperature is self-fixed. So we'll deal with this one. And that makes it pretty easy. I have the change in entropy for the A molecules because they go from V1, initial was V, and the final volume they're able to roam around as V2. In a certain sense, we just have two non-interacting gases, and so I can compute each one separately. They don't even seem to see each other if they're ideal gases because there's no interaction between them. And then likewise on particle B, It likewise goes from a volume V1 equal to V to a volume V2, which is 2 times V. Same number of molecules, and so if you cancel the V's, you'll get a natural log of 2, and you get 2 of them. So the total change of entropy is this expression for that mixing process, again, at constant temperature. And as you would expect, it's greater than 0, and the entropy is increased in this mixing process. Now let's take a look at a case where we have identical molecules. So this is the second case. Really pretty much the same as before, except now I don't have O's. I've got a partition. They're both at the same temperature. I have equal volume on the left and the right. Our initial state has this partition in between, and now the mass of the molecules, they're identical molecules, and so I use the same symbol for these around. And as the systems are really identical on this case. Initial state and the final state, and I can do a similar kind of calculation for the total change. For the gas 1, it goes from V1 to 2V, V1 equal to V to 2V, so I get this. And it goes from V to 2V. It's identical, yeah. The only difference is that the m's are the same. But there's no m in any of these expressions. There wasn't an m on the previous one, right? So it doesn't depend on the masses. Right? So really that calculation is exactly the same. I get nkb times 2 natural log of n. So, and that to a certain extent seems reasonable because there is mixing that occurs amongst these, because particles that were over here go over here and vice versa. Right? The problem comes in this: if you do it from that perspective, we get a positive entropy change. Mixing has occurred. But notice what I can do now. In this configuration, I can easily slide a partition back in between these two. Or if it was a valve or something, so if I slide the partition back, or if it was a valve, well, I can close the valve, and I return basically to this configuration. If I slide a partition back between them, or close the valve from one side to the other, I get the same condition that I started with. And so I'm going from an initial state to a final by removing the partition, and then from that final state I slide the partition back again, and I'm back to our initial state. What that says is that I can reverse the process simply by sliding that in. So it's now a reversible process for identical molecules. And I know for reversible processes, the change in entropy has got to be 0. So in this case, I have at this constant temperature, I have the change in entropy goes back to the original entropy, and then the change of entropy is just 0. And so the question is, well, which one of these is it? Is the change in entropy for these identical particles, identical mass and the ideal gas, is delta S equal to 0? Or is it equal to, like when they were distinguishable, as they got this factor of 2 log 2, which is bigger than 0. So that, in essence, is the Gibbs paradox. How do you resolve it? Well, there's several ways, and as you might guess, it kind of boils around the fact that they're distinguishable or indistinguishable. But what I claim now, it's easily resolved using the Secure-Tetroda equation, and I'll leave that for the next video.